So it is my pleasure to welcome Paul Olsen. He is a longtime friend of mine and of this department. He was a mentor, advisor to Roy Slissa, our structural specialist here. And there's lots of fun facts we could talk about with Paul, but I'll give you a little bit of background. He is from, he grew up in Livingston, New Jersey, and parts of Newark at times. He went to Yale for 3 degrees, a BS, an MPhil, which you get along the way, and a PhD. He was a Miller Fellow at UC Berkeley, and I think during that time you wrote a second dissertation, which
No, it was only a first one.
Oh, okay.
I hadn't finished it. The one requirement of the Miller was that you had to have defended, but I put in a completely undefensible PhD, and then I had to finish it while I was a Miller, having met the minimum requirement.
So, and in the mid-'80s, he came back to the East Coast as an assistant professor at Columbia University. He became a full professor in the mid-'90s, where he is the Stork Memorial Professor of Earth and Environmental Sciences, or Studies, NS.
Sciences.
And he's been at Columbia ever since. I think he spends as much time on this campus as some of our faculty members. He is down here quite often, usually across on Livingston and the core repository. One of the fun facts is he has received a presidential accommodation.
Not accommodation. That's what you get as an undergraduate.
Oh, okay. But
commendation.
Commendation from President Nixon for trying to preserve some dinosaur footprints exposed during construction. What I will say about Paul, and then I'll give him as much time, is this will speak to who Paul is. One Friday night this past fall, I had to go by the repository on my way home, and I was in a hurry to get home. And lo and behold, do I see the door open to 4108 and a strange car or truck with New York plates. And I'm going, oh, well, and so I had to go in and see who it was. And out of the back pops Paul. An hour and a half later, I got home, and he showed me the most beautiful Van Houten cycle, where you go from a dry lake bed to a wet lake bed to a dry processional cycle, all in 2 cores, or 2 boxes in there, and I took a picture of it. But during that conversation, Paul says, I need to give a talk. I've got this new idea, and I need to give a talk so that I can flesh it out. And out of that came Paul's Colloquium talk today. And with that, I will hand it over to Paul.
Thanks very much for that very kind introduction. Yeah, one of the things that Nixon did not give me, fortunately, was the all-expense-paid tour of Indochina. I missed that, thanks to my eyes. In any case, what I'm going to talk about today is this question about volcanic winters related to super eruptions caused by what's called the Central Atlantic Magmatic Province at the beginning of the age of dinosaurs. And this is a really substantial problem, as I'll show you, because you have these things called large igneous provinces, which seem in some way related to mass extinctions, yet the current view is that basaltic provinces, flood basalts, cannot produce column heights large enough to enter the stratosphere and spread globally and cause really large climatic problems. So this talk will focus on what's actually showing up here in this picture, which are 2 airfalls. Well, actually, 3 airfalls, but this one here is snow. This is a volcanic ash that fell in a deep lake, and there's another one up here, and we'll talk about these. And as the volcanic ash themselves, it's not particularly unusual, except in this province, these are the only ones known in the entire province, and that's an important fact. So before I go on, I just wanted to thank all the people who have collaborated with me on this project over the years. We first found this ash more than 10 years ago, and these ashes more than 10 years ago, and it's been highly interdisciplinary work, hitting a lot of different fields, and in a lot of very strange ways, it turns out there's very little work done on these kinds of volcanic deposits. So I'll give you the conclusions first. CAMP, the Central Atlantic Magmatic Province, which is early Mesozoic, Triassic, and latest Triassic and earliest Jurassic, is linked to the end Triassic mass extinction via radiative balance by greenhouse and volcanic winters albedo effects. The Pompton ashes, which are these little airfalls that we'll talk about, provide strong evidence of Central Atlantic Magmatic Province supereruptions, and that's defined as eruptions with greater than 1,000 cubic kilometers of material produced. And aerosol sulfate input testable predictions of sulfur mass independent fractionation. Remnants of ashes are expected around lavas, but maybe not recognizable because of weathering, in situ weathering when it was deposited, and they're called cryptotephras. The effects of the camp at the end Triassic extinction likewise requires proxies of ashes such as epsilon neodymium and PGEs and volcanic winters that should show up as sulfur isotopes and as sulfur mass independent fractionation. Platinum group elements as PGEs. Camp volcanic winters provide a kill mechanism on land for the end Triassic extinction, which is testable by a new project which we floated, proposed to NSF, called DinoDrill. So first, these are the main parts of the talk: the importance of supereruptions, the Central Atlantic Magmatic Province, Pompton ashes as supereruptions, individual basalt flows, flood basalts as supereruption, the ET and ashes, and then the conclusions. So if we look at mass extinction rate through time, and this is a number of marine shelly fossils through time, there are 5 large intervals that show up here. These are called the Big Five by Rapp and Sapkowski back in the 80s, and 3 of them are ones I'll mention today: the end Permian mass extinction, the end Triassic, and the end Cretaceous. And the end Triassic is the one we'll really focus on, and you'll notice in terms of magnitude, it's about the same as the KT. And depending on what metric you use of mass extinction, sometimes it's larger, sometimes it's smaller. It's never, they're almost never, no matter what metric you use, as big as the end Permian mass extinction, but they're still very, very significant. So these mass extinctions correlate in time to a number of what are called large igneous provinces. And on the map of the world for the last 500 million years, you see these various large igneous provinces. The 3 that are tied to those 3 mass extinctions are the Siberian traps, unsurprisingly in Siberia, the Central Atlantic Magmatic Province, which have been split up amongst the continents because of continental drift, and the Deccan lavas, famous for at the end of the Cretaceous. And if you just look at how these compare in terms of volume, estimated volume, and the extinction magnitude, they correlate really quite well. Now, these kinds of diagrams are a little bit deceptive because when you have a given event, I'll pick this one, like the Jurassic Cretaceous, that has to fall somewhere between these 2 other events, right? It's in a linear sequence. It can't fall anyplace else. Same way with the ages and magnitude of these large igneous provinces. So when it's off the line of 1 to 1 like this, it means it's really far off. It's really, but there are 3 of these which are smack on, and when you look at the evidence from each of those igneous provinces and the dates and compare it with the independent evidence of the dates of the mass extinctions, they're exactly on. And of course we know that of these 3, one of them is associated with a giant asteroid impact, which of course occurred at Chicxulub, and we all know the story of that. I won't talk about that. The one I will focus on is the Central Atlantic Magmatic Province. And I'll spend some time talking about why we think it's exactly correlative. And I'll also mention very briefly the PETM and the North Atlantic Igneous Province. So when I say these were big events in the history of life, these were really, really formative events. And so I'll talk almost entirely about what's going on land. I just want to give you a little scenario of what we're talking about. So here we are in the late Permian. The record of the late Permian ecosystems on land is biased towards the higher latitudes, but basically you have a large number of stem mammals, relatives of mammals around both carnivores and herbivores, and a much lower diversity of archosaur reptiles, things related to crocodilians, birds, and other dinosaurs. And then you get to the end Permian mass extinction, and by the middle of the Triassic, the median Triassic, which is really at the beginning of the late Triassic, because the late Triassic comprises most of the Triassic, the world's changed completely, and you have dinosaurs around, large crocodile relatives, and the mammal relatives, the stem mammals, have dropped down to small creatures, our ancestors, scurrying around in the undergrowth trying to avoid being eaten by a dinosaur. Then at the end of the Triassic, you see the extinction of almost all of these guys, and a real takeover by the dinosaurs we know and love. And of course we know these days that almost all dinosaurs were feathered at some point, and then at the end of the Cretaceous, of course, we have the giant impact at Chicxulub, but also the Deccan lavas, and a switch of dominance on land back to mammals. Although dinosaurs still remain an extremely important part of the terrestrial ecosystems, in fact, there are more bird species by a factor 2 now than there are mammals. So in some ways, we're still in the age of mammals. But the world looks different because of these events. So we have the Siberian traps, which have these lava flows, which are shown in the dark green here, and then in these red areas, which are in the subsurface. And this lighter color green are basically extensive intrusives. But in addition, the Siberian traps are associated with quite a large amount of volcaniclastics deposits. In contrast, the end Triassic extinction is associated with the Central Atlantic Magmatic Province, which is much larger in area, but probably smaller in volume, and it has actually exactly zero, except for what I'll show you, airfall deposits of ashes and very, very limited pyroclastics. And then we have the Deccan lavas, which are kind of in between. They occupy a large, I think the battery's going on this. The battery's going. Look at it fade. The Deccan covers this huge area of India. It's very, very thick, and it also has a less significant amount of pyroclastics compared to the Siberian traps. So those are the three units at three large igneous provinces, these flood basalt provinces that we'll talk about. Now, the way they're thought to influence the history of life are by relatively short-term but very intense climate changes. So if you think about a really big, short, but extremely intense climate change, you can think of the KT boundary and the effects that Chicxulub, the impact that Chicxulub are thought to have wrought on climate and through climate life on Earth. So these radiative balance effects are caused largely by two volcanically and climatically important gases, carbon dioxide and sulfur dioxide. They both affect climate via the radiative balance. So CO2, of course, is what's causing one of the major causes of our anthropogenic crisis right now, right? It affects climate via the greenhouse effect and causes global warming. The sulfur dioxide has the opposite effect. It affects albedo. The sulfur dioxide gets into the upper atmosphere, it reacts with water, it produces sulfuric acid, which is highly reflective to light, increasing global albedo, causing global dimming, which causes cooling, and these were named by Mike Rampino back in the 80s, talking about the giant Toba eruption, volcanic winters, and we'll use that term as I continue. So those are the two major effects, and they both have potential to affect global ecosystems. I should mention another effect of CO2 is ocean acidification, which is actually very important in the oceans, but I won't really talk about that. And sulfur dioxide also, via turning into sulfuric acid, also has the possible effects of acidification. So if we look at these two effects, on the left is the effect of global warming. This is the IPCC AR6 estimate, consensus estimate of global warming. So we have this sort of peak of models that predict basically a 2 to 4 degree global on average temperature increase. And on the right we have basically an extrapolation of historic eruptions in terms of sulfur and the projection up to the kinds of injections of sulfur that one might anticipate for large igneous provinces. So 2.5 to 4 degrees for the accepted, it's called climate sensitivity, equilibrium climate sensitivity, and that 2 to 5 degrees applies to a doubling of atmospheric carbon dioxide, whether you start at 180 parts per million or 1,800 parts per million. A doubling from there produces the same, is expected on the basis of models to produce the same amount of global warming. It's interesting to note on this more recent diagram, this secondary peak here, that's much worse. Has much higher climate sensitivity. So then for the extrapolations of large igneous provinces, we're down here. Models predict this for an extrapolation of these the historical eruptions. But all of these are models, right? Just like the carbon dioxide predictions for the future, we don't know how good these sulfur dioxide and albedo effects are. We have no idea, no empirical information, or virtually no empirical information. So we're now going to focus down on our topic of main interest, which is the Central Atlantic Magmatic Province and the end-Triassic mass extinction. So here's the globe. At about 200 million years ago, the continents all united in the supercontinent of Pangaea. This pinkish envelope is literally the envelope of the preserved remnants of this enormous volcanic province. There's been a huge amount of erosion in these regions related to the breakup of North America and Africa, and then South America and Africa. And some of these areas, like this big blob here in Amazonia, are buried below Amazonian sediments. These others here are deeply, deeply eroded. So all of these blobs that you see in darker red are intrusions in this area here that have no sedimentary cover on them. They're eroded way below the level at which there would have been any lavas produced by them. And then most of the lavas are actually preserved in rift basins in North America and Northwest Africa. And in these rift basins in Eastern North America, they're preserved as lavas and intrusions within what's called the Newark supergroup, these Triassic and earliest Jurassic sediments. And the basins that we'll focus on are basically the Newark and, whoops, battery's gone. Let's see if I can get the cursor. Well, maybe I'll just use it less extensively. Okay, so we'll look at this basin here and this basin here and this basin here, mostly Newark and Hartford basins. You all know the camp. That's the Palisades escarpment on the Hudson River, and that's an intrusion of camp magma into pre-existing late Triassic sediments. So the age of that is about 202 million years, and it's intruding sediments that are about 225 million years. But these lavas, and in fact this magma itself, this magma, which is an intrusion, did make it to the surface of the other side of the Newark Basin and erupted as flood basalts. And this is the one that actually connects to the Palisades, called the Orange Mountain basalt. And here it is overlaying strata of latest Triassic age, in which the biological evidence, the fossil evidence for the end Triassic extinction is actually preserved. Now in Pennsylvania, the same lava is present on top of lacustrine strata, which has quite a bit of biological information in it. And superficially, the place that the pollen changes that marks the intriassic extinction looks a lot like the KT boundary in continental sediments. If you've ever seen pictures of the Raton Basin KT boundary, it looks very much like this with a white layer overlain by a coal. So this is very similar looking, and it drove us back in the early 2000s to check for iridium, because after all, that's the paradigm that was so successful. And in fact, we found some. I'll show you that later on, but it is true that this increase in fern spores corresponds exactly to the extinction level of the pollen, which also corresponds to an extinction level in the tetrapod record, the record of land animals. And we have very good stratigraphy of this, and Dennis Kent and Bill Whitty worked out the paleomagnetic strata within the Newark Basin, and that allows us to use this reversal E23R to trace it all over the place. This is the oldest camp lava flow in the basin, the Orange Mountain basalt, and the Intriassic extinction is right below it. We know the age of this very precisely, thanks to the work of the MIT group, which we collaborated with, and got these beautiful zircon dates, uranium-lead zircon drapes, chemical abrasion ID TIMS, that were able to using the astrochronology from the lacustrine strata, which I haven't actually talked about yet, but you'll see these wiggly lines that are associated with these lacustrine sediments. And we're able to show that the Triassic extinction in these rift basins is at 201.564 plus or minus 0.015. That's 15,000 years out of 200 million years. Remarkable degree of precision, and we think pretty close to being accurate as well. And when you compare these dates that we got back in 2013 with a whole bunch of new ones, newer ones that come from all of the Camp Province, and dates from ashes interbedded with marine deposits, you can see that the Triassic extinction, as we determined it, actually falls right in where you'd expect it, on the basis of the dates from the lower precision dates from these ashes, which are also chemical abrasion ID TIMS from Peru. Now, this colored package you see here is not a cartoon of the stratigraphy. It's actually a digitized version of the color code based on almost entirely, in this case, cores. So we know this stratigraphy extremely well, and these cores, by the way, are over in the repository on the Livingston campus. So this wiggly line that you see, there are two sets of them here. One is a curve derived directly from these strata. The other one is an astronomical solution projected backwards to 202 million years ago. And they're very, very, very similar. And one of them is empirical and one of them is theoretical, but they match very closely. The main lava flows of in the basins are these three events that you see here. So all these uranium lead dates really give us a very little time there. There's less than 1 million years in there. Think about that. This represents less than 1 million years. And we know it really, really beautifully. So then, looking at a slightly larger scale, Morgan Schaller, who was a graduate in the PhD program here, he used these same lake sediments, these soils, when the lakes would dry out, used the carbonate proxy of CO2 to derive this very, very high resolution atmospheric CO2 proxy record, and it turns out that each of the lava flows sequences corresponds to a doubling to tripling of CO2, right? So that's that first gas that I was talking about as being important to the radiative balance. So you'd anticipate that since you have let's just say a doubling, that you'd have an increase in global temperatures after each of these sets of lava flows that would correspond to a 2.5 to 4 degree increase in global temperatures. And then there's a fourth one that shows up, which we don't have any lava flows recognized yet for, but we don't have everything dated either. So you have this increase in temperature. It's not clear how that would affect land life. certainly animals that live in the tropics could migrate poleward to escape the warmer temperatures. But there's this other gas, sulfur dioxide, and a legitimate question about these is you'd expect to have volcanic winters if you could get the volcanic products, ashes, and sulfur high enough up in the atmosphere to go over a large area and produce a powerful volcanic winter. And a legitimate question is, could they overwhelm the effects of global warming caused by the CO2? And the answer is evidently. So this is a model published recently of pulsed forcing. Each one of these represents an eruption of one part of the Central Atlantic magmatic province over 1,000 years. CO2 input is shown here. Here's that rise in global temperature predicted by the doubling of CO2. But the expectation is that the sulfur aerosols would have a much, much larger effect over a much shorter period than the carbon dioxide. So you can see the temperatures go up, ramp up, and then you can barely see it decline, while the drop in temperature is very abrupt. And the more concentrated you make this input of sulfur to a certain extent, the larger the predicted temperature decrease would be, to the point we'd actually anticipate freezing in the tropics for short amounts of time. Now, does the Central Atlantic magmatic province actually have enough sulfur in it to do it? And the answer apparently is yes. So here a comparison of a bunch of mostly historical eruptions and one at the Paleocene-Eocene boundary called Fur, which we'll come back to later. And here are the Deccan, the Parana and Ekadeca, and the Central Atlantic magmatic province. And you can see the sulfur levels are really quite comparable, including to that of Latki. And Latki was the eruption that basically had a big role in the cause of the French Revolution, in which there was what's called a dry fog all over Europe, caused crop failures and so on, which combined with mismanagement resulted in the death of about 6 million people in the Northern Hemisphere, making it the largest natural disaster ever to occur that we know of in terms of number of people killed. So yeah, so we have these two possible causes of climatic disruption: the doubling of CO2 from the eruptions, and then the cooling effects from sulfur dioxide. Now, is there any evidence of these volcanic winters? And that turns out to be very difficult, because there basically is virtually no proxy for this kind of process for the sulfur aerosols, and temperature is famous for being hard to get at in the geological records. So we're going to talk about these things called the Pompton ashes. Here's these basins that we'll talk about: Newark and Hartford, and to a lesser extent Deerfield. And here are these stratigraphic records. In the case of Hartford and Newark, you see it says all core for the Newark, almost all core for the Hartford, almost all outcrop for the Culpeper, and all outcrop for this Deerfield basin. And here are the three major pulses, and there's a minor pulse called the Hickory Grove, and here's the time, and here's the astrochronology. And we're going to focus on these two basins, and this cycle here. The discovery spot was in the Hartford Basin, and it was in the town of East Berlin. These dots are places that these ashes are known from. There are 10 sites spread over 200 kilometers from 4 cores and 6 outcrops. There's no important change in thickness or grain size, which we'll get back to in a moment, and no plausible local source. So here's the discovery site, this beautiful road cut in East Berlin, Connecticut. For reasons I don't understand, in Connecticut they don't cover up the rocks with fake rock or soil like they do in the Newark Basin. And so this outcrop's been here since 1983. And you see a black shale here, and a black shale here, and a black shale here, and a gray shale here, and a red shale here. These are 20,000 year Van Houten cycles. And you have a deep water interval at each one of these black shales. And one of them, this one right here, has these volcanic rocks we call the Pompton, these airfall deposits we call the Pompton ashes. So here's that cycle going from basically soils to shallow water lakes, to deep lakes, to shallow lakes, to soils again. Then they're part of this larger cyclical sequence, and these have lots of fossils in them, dinosaur footprints in the very shallow water lake deposits, a lagerstätten or a special preservation type of deposit with fossil fish and things like that, and then you go back into footprints into shallow water lake strata. And it's this bed that has the ash deposits in it. And what it looks like when you get up close is this beautifully laminated, carbonate-rich, organic-rich deposit, typical of a lake deposited that was deep compared to its area with no oxygen at the bottom. So there are these wonderfully preserved fossils. This is a fossil fish from that exact location. And in this case, it's this very peculiar process called dephosphatization, where almost all the mineral part of the fish is gone, leaving an organic residue, in this case just a thin film of calcite associated with it. Getting close to the border fault, you get much better preservation like this. And in the Newark Basin, the same lake cycle produces fossil fish. And these are interesting. They're completely dephosphatized, but the pigment is still preserved in the eye and parts of the gut, which is quite interesting. You'll see that again later on. So the very first place we saw these ashes was this outcrop, which was the tidal slide. And this red layer is red because of jarositic minerals that form from the weathering of pyrite in the ash. The ash at this place is about 20% pyrite, which is not part of the ash. It came in afterwards. And so there's one ash there, and then that's the Pompton ash 1, and then Pompton ash 2 is much thinner and above that. So these things have phenomenal lateral continuity. These are XRF traces across these units. Notice the scale here is in centimeters. At the ashes, there is a large amount of iron and sulfur, which is the pyrite. In the little ash has the same thing. One of the things you can see when you look across this over 200 kilometers of traverse is very, very little change. Notice that these two are in the Newark Basin, and these are in the Hartford Basin. And from the, I don't have a thin section here, but from the southernmost location to the northernmost location is over 200 kilometers. Now, I'm a simple-minded guy, and I mean that seriously. I like to see things simple as possible. And an impromptu meeting in front of the Geoscience building at Lamont last year, I had brought out 2 samples of the ash and just put them next to each other. And this shows you what I'm talking about in terms of a very simple way of seeing how similar these ashes are. These 2 samples, one's in the Newark, one's in the Hartford Basin, and they're 142 kilometers apart.
Was that far apart back then?
Yes. Yes, because it's a single plate. So that's, I think is pretty graphic. So when we look at the chemical constitutes of these ashes, we don't have them completely done. The second ash wasn't even realized to be there. In fact, when Sean interviewed, I showed him this ash at Columbia when he interviewed for a PhD student, Sean Kinney over there in the audience. Right, yeah. So he said, well, what about this thing up here? That looks kind of similar. I said, nah. Well, he was right. It was a second ash. And you can see the sulfur. There's interesting data from sulfur isotopes, which I'll talk about in a moment. Here's pyrite going up to about 17% in this particular sample. There's a mercury anomaly. There is a platinum group element anomaly, including iridium. and an epsilon neodymium anomaly. And epsilon neodymium is important. Epsilon neodymium is basically the deviation from the expectation of the samarium neodymium system from basically the evolution of a chondrite. So a meteor. So when it's more positive, it's a mantle-like, and it's more negative, it's more continental crust-like in terms of the deviation from which you'd expect from the evolution of a chondrite. And as I said, the ash has 10% pyrite, and it's important to worry about, because what that pyrite is telling you is that sulfur reduction, bacterial sulfur reduction, was occurring actively in that little ash after deposition, because this didn't come from that amount of sulfur didn't come from the ash. And that means there was a redox boundary associated with that. When you have redox boundaries, you have the potential for that surplus of electrons to drive the migration of metals into that layer, towards the boundaries of that layer. And so we have to worry whether or not this is a diagenetic feature and not indigenous to the ash, although other ashes, as we'll see, are known to have iridium anomalies. And we think that maybe osmium isotopes might be a way to get at whether this is as actually redox or something, or whether these are indigenous to the ash itself. There's no reason to think that the epsilon neodymium would behave like that. And we put this in a larger perspective. Here are these two sequences. Here are the Pompton ashes in terms of epsilon neodymium, and you see they're driving themselves out towards the basaltic range, and here's the lava flow that's on the top, the Hamden basalt, and a lava flow at the bottom, the Orange Mountain basalt or Talcott basalt. Now I've shown these in these diagrams as if there's no time involved with those, except over here you see this Preakness upper flows. This was something realized only recently, that there were lava flows being deposited in the Newark Basin during time there was sedimentation going on here in the Hartford Basin, something that'll be important later on. Now, when we look at this in terms of rare earth elements, I'm really getting out of my league here, we see the Pompton ash looks like average pyrite in shales, with a strong negative europium anomaly. It looks like average Newark sediments. In other words, it looks like continental crust, which is not what you'd expect of an ash. So we think that's due to exchange with the surrounding sediments and the surrounding interstitial water during diagenesis. This is the recurrent basalt, Hamden basalt and Hook Mountain basalt. They're above the Pompton ashes. They have a very flat-looking spectrum, the very small europium anomaly. And they're more andesitic in composition than pure basaltic composition. So let's take a look close up. This is a large thin section of the two ashes. This is the first one, Pompton Ash 1. This is Pompton Ash 2. This shows the sulfur, iron, calcium. And if we focus in on that lower part, just look at the bottom, you know the ash is graded. It's very obviously graded. When you look really closely, so here's 1 millimeter, you see these little spherules all over the place, and every so often you'll see a big phenocryst of plagioclase here. This is not across polars, past nickels, so you can't see it. It's just, I wanted to show in natural light, but you have all these spherules all over the place. The black is pyrite. If we look at this, in a backscattered electron image, here's one of these big plagioclase laths. Here's a smaller one, and here's one of these spherules. Now, in composition, this has almost been altered to pure albite. This one here has an albite rim and a more calcic interior based on microprobe analysis. Here are the actual data, with orthoclase up here, calcium feldspar, sodium feldspar, and calcium feldspar there. And if we zoom in on this, on that spherule, it looks very much, actually, interestingly enough, like an impact spherule. And it seems to have this radial pattern of crystallite, suggesting that it has a strong quench texture and had been up way high in the atmosphere. And you got all this ground mass of lots of little tiny crystals, and here's that big plagioclase crystal here. So now we wanted to do an experiment. This is results from Morgan Schaller, which you'll see in a moment, is if these ashes were produced by an eruption which had a column height large enough to drive sulfur dioxide real high in the atmosphere, spread globally and cause the volcanic winters, you would anticipate that it would get cold right after this. And that should show up in some temperature proxy. And one of the simple temperature proxies to do would be oxygen isotopes in a freshwater system. So we did this, and Morgan sent me an email with these results and said, this is not what we expected. So in fact, as you can see, the temperatures are relatively low based on the oxygen isotopes. They get higher right below, and then they're high right above, and that's not what we would anticipate at all. And I thought, oh, this is not making much sense, but then I realized there's a problem with taking these measurements, a really big problem. So let's zoom in on this lower ash. The problem, so now this is the transition from the primary airfall itself up to the more normal looking very finely laminated sediments. The problem basically is that when you get an organic laminae here, just like this one or this one here, this means there's a pause. You have lake productivity is high, organic material settling in, and so these deposits, these are not, this one and this one are not actually part of the airfall, or this one. And they actually show up when you look really closely. You can find mica grains and quartz grains and things. There's no quartz at all in the actual airfall. So these laminae here have no indigenous carbonate. Zero. We think the carbonate factor is off because it was cold. But there is some measurable carbonate in there. What is it? It's a cement. In other words, it's something filling in the interstices after deposition. The cement is coming from above. So it doesn't record what the temperatures were when these layers were being deposited. But it's interesting that you have these layers without any indigenous carbonate, because that is what you would expect of a lowering in temperatures, which would lower the evaporation of the lake, which would drop the lake down below the concentration at which the limestone would precipitate. The carbonates are not fossils. They're not like forams or something like hoccoliths or something like that. It's direct precipitation from the water column. So that's not happening down here, just like it's not happening here. Unfortunately, we didn't have any measurements from in the ash itself, but the prediction would be that it would be reflecting the cement values, which would be these temperatures that were existing after it warmed up again. In fact, one of the things you do see that's a prediction of exactly this scenario is that there's an especially thick lamina of carbonate after these few 6 or 7 years of carbonate factory off. It gets warm again, water evaporates, and this carbonate that's been accumulating as calcium ions and bicarbonate ions and dissolved carbonate in the water column now evaporate. Now the water's evaporating and it dumps out and overshoots what it would have done otherwise. So that's what this thick laminae is. Well, this system gives us a very nice little experiment because there's another ash. The other ash looks the same. Again, you have the primary airfall ash, a few years of carbonate factory off, and then an overshoot with a lot of carbonate dumping out. Now, we don't have measurements on that yet, but the prediction would be that it would be warm looking as well. So this is sort of background already back to normal. Each one of these couplets of a dark versus light, and these are flocks basically of carbonate that were deposited out of the water column, which you don't see in the ash. And so we can estimate what the duration is between these two ashes, and depending on what you want to pick as a couplet, is non-trivial, you get between 37 and 94 years between these two events. Okay, so that's the basic scenario and composition of these ashes. Where did they come from? If we look at thickness trends from Newark Basin to Hartford Basin and around the Hartford Basin, there's basically no thickness trend. The average is about 5.5 plus or minus 1 millimeter for the lower ash, but no trend. And this shows up most obviously in this, right? Where you have the instrumentally measured thickness of the ash from the XRF, sulfur, iron, and carbonate measurements. I think the variance and the variability that you saw in the measurements in the previous diagram were basically from measurement error. Because it's hard to put your finger on when you put a little caliper up against the ash, but it is. And it's not, we didn't do it yet with these measurements. This is much more precise. You can actually see the difference between the true ash, which is here to here, versus these laminae that are the few years when the carbonate factor is off. You can see the difference. You can measure it much more precisely. I think these are all the same scale. There's basically no change in thickness over 200 kilometers. Now, that said, what do we know about modern, what's the expectation for a volcanic eruption and the ashes? Basically, the ashes fall off in thickness away from their source exponentially. And it's actually multiple exponential. And it's a multiple exponential because there are different processes when you're really close to the eruption versus further away that are operating. So first you have these big lumps coming out of the sky, right? And then by the time you're way out here, you've got stuff coming out as a fine dust. So there are different kinds of physical processes involved, so you get this multiple exponential. This is a Pinatubo, 1991, Mount St. Helens, and the famous eruption, which I will not attempt the pronunciation of. I've looked it up over multiple times, multiple years on YouTube, how to pronounce this thing. And you see this chuckling Icelandic person, oh, it's simple, blah, 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 blah. And then, it's not simple.
E13, E with 13 letters. That's what
right. So the little gray bars here are the distance over which you would expect to get 5.5 plus or minus 1 millimeter. Notice that this is 100 kilometers. Here's 100 kilometers. Here's 100 kilometers. The distance over which it's expected to be constant from a point source is basically inconsequential. These bear no resemblance to what we would anticipate. Here's the actual distribution of the Pinatubo ash in thickness compared to the Newark Hartford Basin. And you can see, just going from here to here, you have a predicted doubling of the ash thickness. And it's a 5-fold decrease over this distance. There is no position in which you can put the Newark Basin in here except for the miracle position, which would be both these would have to be parallel to the lines here that would result in no change over 200 kilometers. If we look at the two basins again and say, well, what about something that isn't a miracle position? What if you have a dike, a feeder for these eruptions and the flows that is basically directly between the two and parallel to them? Yes, you would then anticipate the thicknesses of the ashes to be the same, providing they wasn't strongly asymmetrical like Pinatubo on both sides. The trouble is that we know something about the intrusive plumbing system in this region. It's mapped, and these little lines are all the dikes that are known, and there is one, in fact, that is a feeder right here to the younger basalts, the Hamden basalts, and there's another one for the lower feeders down here, but they're not the right age at all for the Pompton ashes. We know this can't be. We know it can't be because the Hamden is on top. And over 100,000 years younger in physical stratigraphy and superposition from the Pompton ashes. It cannot have produced the Pompton ash. You can see where it intersects in the field. Okay, and that's right here, right in Massachusetts. So this diagram shows these older lavas at the stratigraphy of these Jurassic lacustrine deposits, and here's the Pompton ash in the same exact lacustrine cycle over these two basins. And the age of that Pompton ash we can't get from the ash itself because there's no quartz. It's not felsic enough for there to be zircons. There are no zircons. The plagioclase are these little tiny grains that are really hard to date, and even if it wouldn't really help because the precision on that would be less than the zircons that we have from here and here. So if you interpolate between these two uranium-lead chemical abrasion ID-TIMS dates and use the astrochronology, you get an astrochronological date of 201.5. So where does that fall in our array of uranium-lead dates from the rest of the camp? It turns out it falls very nicely on top of one dike, the Fumzug dike in Morocco, which is one of the two giant dikes in Morocco. Fumzud is it's gigantic. It's truly gigantic. Here it is, and these are sills that were fed by the Fumzud, and this is probably related to the youngest basalt in the Moroccan basins called the recurrent. Now, it turns out that if you look again at the trace elements and various trace element ratios, the different lavas array in these graphs in time. So this one at Mali is the oldest, and they get progressively young as you move in this direction. That's ocean floor. And here in this graph, it's in the other direction. Basically, the chemistry tracks time based on uranium lead, like this, and the Fumzug-dike plots with these younger units. So in terms of these trace elements, the Fumzug is a suitable source for the Pompton ashes. If we now look at all these different preserved remnants of the Central Atlantic Magmatic Province, they have some Zugdike about 1,500 kilometers away from the Newark and Hartford Basin, and they'd be in appropriate position to feed these ashes based on the winter monsoon winds. What's comparable to that? You need a supereruption. So here is a Yellowstone scale supereruption modeled by Masson et al. Here's the predicted drop-off in thickness with distance. And the 7 millimeters at 1,500 kilometers is sort of the average prediction of what the ash would be. The Newark Hartford Pompton ashes fall in that position, and you'll notice that that stays within that range over 120 kilometers. So we're getting in the right order of magnitude here, but that would have to be one of these supereruptions. We can make a quick comparison to a place where we have a lot more ashes to ask the question, is the frequency of these two ashes, the Pompton ashes, they're the only two airfalls known from the whole Camp province. Is that actually a reasonable expectation of their frequency? The short answer is yes. Here's the North Atlantic Igneous Province in the position of continents during the early Eocene. And here's a place called Fur. This is the Millville core, which is very famous for having spherules from an impact PTM discovered by Morgan Schaller. Here are lava flows of the Nape in Greenland. It's a flood basalt province. And here are these diatomites, which have this nice structural complexity thanks to glaciers in Denmark shoving this stuff to the south. And if we look at the aggregate thickness of the ashes over this region, it falls off very much the same way as we saw the supereruption of Yellowstone. And if we look at the island of Fur and look at those ashes, this is what you see. You see a lot of ashes. Every black line you see there is an ash. This is what one of them looks like. So these are these laminated sediments. Here's this graded volcanic ash. The sediments, just like we saw associated with the The Pompton ashes have these beautifully preserved fossils with the pigments in the eye and the gut. There are also these, though. Those are glendonites. Glendonites are pseudomorphs after ichthyoite, which is a type of calcium carbonate that forms under low temperatures. And for the fur formation, these are estimated to be produced at about 5 degrees C. This is just before the Eocene climatic optimum. It's supposed to be really warm. That's not warm. So here's a section of the fur formation with all these ashes. Here's the PETM excursion. This is, you see the dates here, the Eocene climatic optimums up here, and the frequency of these ashes are 4.9 ashes per 20,000 years up here. Based on this accumulation rate, 1.8 ashes per 20K. These are a bunch of dates from those ashes. There are also iridium anomalies. The Pompton ash level is at this level. You can see that many of the ashes in the fur formation exceed that. So it is possible these are indigenous. If you just do a quick back-of-the-envelope probability calculation, you would say the chances of getting, based on the distribution, if you just assume that it's only in those very finely laminated deposits that you get the ash preserved, you find that the probability of getting one of those ashes in the strata is only 22% for most of the fur formation, and at the PTM only 8%. So, from that you can say you can't distinguish between the probability of getting these ashes preserved, what looks like very rarely, in Eastern North America versus the fur formation. So there are various proxies we could look at. I'll go through these very quickly because I can see I am running out of time very rapidly, if not even out of it. And the sulfur isotopes, delta S34, in pyrite from these layers show something very interesting. In the sediments above and below the ashes, you have a negative, very strongly negative values of the delta S34. That's basically what we think as a consequence of greater discrimination by the sulfate-reducing bacteria allowed by abundant volcanic sulfate. And if those of you are familiar with PCO2 proxies, it's basically the same as the argument that high PCO2 results in greater isotomic discrimination in photosynthesis as recorded by plastic tissue. It's the same kind of process. And we look at this in terms of the cycle in which it's preserved. This is the work of Eva Stoican. These are two different cores in the Newark Basin showing very similar results. Here's the Pompton ash. The Pompton ash was not measured in the blue line here. This is, of course, the Hartford Basin, but we expect, in fact, we have data that shows it's exactly the same. And you see this negative excursion. So that, we think, as I said, is due to this greater discrimination, due to abundant sulfate added from aerosols falling out from the eruption that are fertilizing the water column, and that extra sulfate's diffusing into the sediments, and then bacterial reductions having its way and not doing much discrimination. On the other hand, above it, you get this very strong positive excursion, which is an effect of evaporative concentration of the sulfate and a reservoir effect, very much like the biological pump, basically driving towards positive values. Now, this makes a prediction. So I'm all about predictions. I want predictions and tests. The prediction here is that if you really did have an eruptive column that went up into the stratosphere and spread out, you would expect to see the sulfur isotopes undergo what's called mass-independent fractionation, just like they did back in the Archean when there was no oxygen in the atmosphere and therefore no ozone shield. And so photodissociation could drive this mass-independent fractionation. And I'm not going to go into this diagram in detail. All that's necessary to take out of this is if you have this volcanic plume, this cap delta S33, which is the deviation from what you would expect from a mass-dependent fractionation, would then play out in and this is well known for the present day, play out above the tropopause, above the ozone shield, in this mass-independent fractionation, and the deviations would be positive in one place and negative in another, but the last thing you'd expect it would be to be 0. So that gives us an expectation. Oops, that gives us an expectation. Sorry about that. That gives us an expectation. Oh, I did that right. There we go. That we should see that recorded in the Hartford Rift Basin, in which the standing reservoir of sulfate's relatively low, and you could see that mass-independent fractionation, versus, say, an ocean record in which the reservoir of sulfate is so large that it would dilute any effect from the mass-independent fractionation. So this is a clear prediction. And we've enlisted Shuhei Ono at MIT to look for this sulfur mass-independent fractionation. Now, we don't know the answer yet, but this is the expectation. And this is super important, because if you speak to people who work on sulfate aerosols right now, they'll tell you we have no evidence that basaltic eruptions can produce column heights large enough to have this effect. Now, there are also biological proxies, which I won't go into. This is a fern, which is rather common only directly after the lava flows, and we think it's a proxy for cold. So now, if we look at the lava flows themselves, let's look up. Sorry about that. Let's look at these here. These are an extremely large lava flow, what we call Preakness Flow 2. That has this very distinctive fracture. Here it is in the Newark. That was the Hartford Basin. Here is the Newark Basin with Martha Witzjack for scale in 1984. This is in the Culpeper Basin. The Culpeper Basin one gets to be over 200 meters thick. One lava flow. It's perhaps the thickest lava flow in the world. In terms of effusive rates, that's 25 to 250 cubic kilometers a year. And in the scale of things, the red bar is where it fits. And so you can see that on a scale of decades, that one lava flow of the camp, of which there are many, is enormous. It's many orders of magnitude, several orders of magnitude, not many, but several orders of magnitude greater than Kilauea eruption. For comparison, this is 2,400, let's say, cubic kilometers of basalt. Latke, causing 6 million deaths, is 15 cubic kilometers. So the tops of the flows, we think, might catch the ash. One proxy of that might be mercury. I think there are problems with the system, but if we look at the ash, here's two locations, one in the Hartford, one in the Newark Basin. There is a mercury anomaly associated with the ash. If we look at tops of lava flows, we see this is a modern one, Sunset Crater, and here we have contact between two flows in the Newark Basin with this highly irregular upper surface which could trap material. Here's the caldera surface of Kilauea Iki. Again, big cracks in it, trapping stuff. This is the Orange Mountain basalt in the Newark Basin, and these are sediments in a blister. So this is lava of the same flow as down here, and this is the second flow on top of it. So we have any evidence of this? Yeah. Well, here's the contact between the uppermost basalt in the Newark Basin and the sediments above it. This is the basal contact. There is a mercury anomaly associated with material that's infiltrated the top of this flow. That may be from ash. It could also be from diagenesis, and because mercury is attracted to both organic matter and pyrite. So what about the ETE? So I'm wrapping up here. So the end-Trias extinctions, the big kahuna here, we want to understand whether this extinction was caused by these sulfur aerosols and the volcanic winters. We saw this section before. Here's the end-Triassic extinction layer. Here's the iridium anomalies associated with this. There are multiple ones. We think they're diagenetically focused, but we think there's maybe too much iridium to be exclusively from that, and some of them were from ashes. So we could approach this by looking at these other proxies. We can approach this by looking at sulfur isotopes, and we're hoping to be able to do this. So here, by looking at, say, the osmium again, right? If the platinum group elements were concentrated solely by diagenesis, the osmium isotopes in what we think were ashes should be the same as what's above or below, but if the platinum group elements are indigenous, then they should be different because they're of mafic origin, not continental. So here are more of these platinum group elements anomalies. So we're hoping to get evidence about this, but we need tests. A test that we're proposing is to core the East Berlin Formation here and get fresh material for what's called the Dino Drill project. So that would be in the Hartford Basin, located near Hartford, at famous Dinosaur State Park, where we have these wonderful dinosaur footprints, where we have this uppermost lava flow and the lower flow, and would drill down through this section at Dino Drill, about 400 meters of section. It's already been proposed to NSF, to Frontier, what is it called? Frontier something in the earth sciences. Anyway, I can never remember what the acronyms stand for. But we make a bunch of predictions, and we can test these by these drill holes. There's the sulfur independent. Here's the sulfur isotopes that I showed you before from this here. This is what we would expect of the record of sulfur isotopes. We only have data from this one, from this excursion. We have a variety of, and of course we'd look at sulfur mass independent fractionation, which would be the big indicator. If we see there's sulfur mass independent fractionation, the only reasonable interpretation of that is a huge high basaltic column involved with these eruptions. And these are a bunch of predictions that we make and tests that we make based on Dino Drill. So again, the conclusions, they're here. Camp is linked to the Triassic extinction. Pompton ashes provide strong evidence of a supereruption. Remnants of ashes expected around the lavas, but maybe they're not recognizable because of weathering. And the effects of the camp require proxies that we've talked about, like epsilon neodymium. And camp volcanic winters provide the mechanism for the extinction on land, allowing the feathered dinosaurs who were pre-adapted to cold conditions because of their insulation to survive these volcanic winters. It wasn't the heat of global warming, it was the cold. Because if it gets warm, you can move poleward where it's cooler. But if it gets cold and you don't have adaptations to cold, you have nowhere to go. And so here's a view from New Jersey with a feathered early carnivorous dinosaur with one of our ancestors in its mouth. And of course, during the eruption of the camp, and you can see the lavas erupting in the background here, I have it snowing. Thank you. Sorry for going over there. So, if those of you who have to leave, by all means leave. And questions? Let me go back to refresh your memory. Because that's one thing, when in talks like colloquia, I can never remember what the questions were by the time I get to the end. Greg.
I was just going to say, thank you. I love that talks bring us right down to the fundamentals of looking at the details at outcrop level or even below. And it got me to thinking, how deep do you anticipate the lake was where these ash beds fell? And then I'll have some follow-up.
Okay. How deep? The question was, how deep do you anticipate the lakes were where these ashes fell? I would guess on the order of excess of 100 meters.
But they had to dry up entirely. Is that correct?
The lake cycles dry up entirely. Yeah. So at times of maximum insolation, at minimum precession, you get the strongest monsoon rains associated with that, and that floods the basin. You get these deep lakes, and then at times of minimum insolation, they dry out completely. But when I say completely, it means they actually dried out many times, but they also had a little bit of water in them many times as well. And there's still sedimentation going on from aeolian processes, for example, like dust.
Did I understand correctly that the carbonate cement for these had to come from above?
But only at the scale of millimeters. Well, before compaction, it was probably the scale of a centimeter or so.
Alan Robach has a question.
Yes.
Yeah, he has to type it in the chat.
Okay, what's the question in the chat? Let me see. I can't see the chat here.
Alan, I think you can just talk, and he can't hear it, I'll repeat the question.
Can you hear me?
I can't see where it is here.
Can you hear me?
Yes, I can hear you, Alan.
My question is, volcanic aerosol clouds only have an enfolding lifetime of about 1 year.
Yes.
Even if there was a big volcanic cloud, how could that produce a mass extinction?
Can you repeat that question, because I can't get close enough to hear it?
He said the volcanic ash clouds had the short time in the atmosphere. He said, how can that produce the mass extinction?
They wouldn't. You have to have one after another, after another, after another, after another. The amount of time, and you know this, thank you for asking that question, right? That you maybe the cold would hang around for 5 years, maybe less, after each eruption. But remember that some of these eruptions, the way we think about these eruptions, we think about an eruption taking a few months. Suppose the eruption took 50 years and was putting out sulfur dioxide for that whole period. So it would be loading the atmosphere and it would be coming out of the atmosphere, it would be loading the atmosphere and coming out of the atmosphere. So presumably the volcanic winter would last on the scale of 50 years, right? And then after 5 years after it stops, then it would get warmer again. But then you might have another one, and another one, and another one, and another one, which is the way it was modeled by that guy Landweers. A very good question. It's absolutely radically important. There have to be long duration eruptions and many of them.
And is there evidence for stratosphere?
And you can only put so much sulfate into the atmosphere anyway.
I'm sorry, Alan, can you say again?
Is there evidence that these stratospheric injection lasted for that long? We don't know of any examples of that, even from supereruptions, that it would continuously get into the stratosphere.
The question was, do we have any evidence of these eruptions lasting for that long? And the answer is absolutely not. Our record, our empirical record of basaltic eruptions are limited to these incredibly wimpy little things like in Iceland or Hawaii. And nothing as we have ever experienced are like these Central Atlantic Magmatic Province eruptions, which have 2 to 3 orders of magnitude larger eruptive volumes that we do know of than any historical basaltic eruption. So the only way to know if these eruptions had column heights that could get into the stratosphere would be from this mass-independent fractionation, and then maybe around the lava flows where unfortunately the basaltic ash will weather away to nothing, basically, could leave some chemical tracers in other forms, and we can get at this, get at whether they really did this or not. So I'm posing these as hypotheses and trying to find tests of those hypotheses, but the important and critical feature to remember is we have no experience, no empirical experience with these kinds of eruptions. Very good question, very helpful. I was hoping you'd be here, Alan. Yes?
Do we have ashfall in Morocco?
Do we have ash falls in Morocco? So the problem that we have, here's the problem we have. These are basaltic ash falls. Their main components are plagioclase, right? If that lands in an environment that's a soil-producing environment, or even an environment that sloshes around the sediments a lot in the oxidative environment, that stuff's going to weather away to zero. And since most of the environment in which these basins existed and produced sediment were not these deep lakes, where you have a chance of preserving these airfalls, but rather soil-forming environments, we don't see anything at all. So we have to look for the proxies and understand how to recognize the ashes that used to be there on the basis of the proxies. So the answer is no, there's no evidence for direct evidence of these kind of airfalls in Morocco, unless it are these iridium anomalies and mercury anomalies. But there are other ways to make them, so you've got to find ways of excluding those other mechanisms. And just, again, find tricky tests, find ways to exclude other processes as you look at these things. But we don't know the answer to that yet. That's why we got interested in these ashes for exactly the reason you're saying. If we take a place we know there's an airfall, what do we see? And can we then make conclusions from that and look at areas where we think it might be a weathered product, a cryptotephra, of one of these airfalls, and see if we can use that information there. And that took us down that rabbit hole.
One last question, or?
All right, well, thank you very much. I appreciate your indulgence.